All right. Thank you for showing up in class. I would say this lecture is the most important for your life because, as the Beatles talk about, we're going to talk about relationships in this life. And if you only take one thing away from this lecture, if you're a man, you should learn that mathematically it's very important to ask the woman that you love out. We'll show that. We'll prove it here. And if you're a woman, it's very important not to wait to be asked out. Because if you do, as we'll show, you'll end up in a stable matching perhaps, but it'll possibly be the worst stable matching for you. So both of these will be mathematically quantified in certain ways. So today's lecture, we're going to talk about this special algorithm. It's called the stable matching algorithm. It was studied by Gale and Shapley in the 1960s in the context of an economic matching problem. And later on, this guy from Stanford, Alvin Roth, studied this type of matching as it applies to many types of markets. And in 2012, basically Shapley and Roth won the Nobel Prize in Economics for this type of work. So that's the foundation of this type of algorithm. And the basic problem is this. Okay, so let's consider again our favorite students and our favorite schools, and imagine that we have to assign these students to their colleges. But unlike the case of bipartite matching, where we just put some random edges between these things, let's consider a more realistic model of matching in this situation. So imagine that what we have is on the left here, we have their top preference. That's the school that the particular character there would like to go to. And here on the right is going to be accept list, where they were accepted. Now there is a little bit So, for example, the mouse was accepted to Harvard and Virginia, the dog, Yale and Harvard, the cow, Virginia, Harvard, the fish, Texas and Yale. And now we'd like to assign students to their colleges such that we'd like to somehow come up with a maximum global matching. So certainly the individual students can only be matched to places that they've been accepted, but we'd like to try to give them their top preference whenever possible. Okay, so in this particular case, since the mouse was accepted at both of these places, we can certainly give them their top place. Here we can give them their second place. We can also give them their top place. So if we were to make this particular matching, for example, only 3 of the players would get matched. But if we were to switch these 2 edges, then all 4 would be able to get matched. Right? So the problem in this type of matching we're going to characterize as follows. So there are a set of, and the literature on this basically phrases every type of matching as a matching between men and women. So we'll just stick with that, even though times have changed. So we'll have a set here of male participants, M1 all the way through MN, and a set of women, W1 through WN. Okay, and so these are the two input sets, and a matching S is going to be a set it's going to be a set of pairs and it's going to be a matching So it's going to be a matching just like with bipartite matching. If these pairs, Mi and Wj, each Mi only occurs in one pair and each Wj only occurs in one pair. So recall in bipartite matching we had a left side and a right side, and a bipartite matching was a set of edges where each node only occurs once, right? Each edge only is incident on one node. Similarly here, we can look at this set S as just a set of edges as well. So we're looking for a set of edges between the left and the right, such that each node only occurs in one pair, and the matching is going to be perfect if it's going to be exactly the same size. So if there are n men and women participants, the matching is perfect if there are n pairs in this set. Okay? The additional input that we're going to get, in addition, so unlike the bipartite matching, the thing that's different about a stable matching is that we get preferences this time. So if the set of M is M1 through Mn, each Mi has a preference so each Mi is going to rank the women in W. And the way we're going to say that is we're going to have this little special operator like this, okay? And this basically means that Mi prefers W2 to W1. Right? Okay, so for example, in this situation, and this relationship, it ranks all of the elements of W. So each Mi ranks all of the members of W. And similarly, each Wj is going to rank all of the elements of M. All right, so here's an example. So in this particular case, this is the set M, this is the set W, and these are their preference relationships. So each element in M is going to rank all of the elements in W, so here the dog prefers UVA to Harvard, the cow prefers Harvard to UVA, etc., etc. So everybody, does this make sense to everybody? Okay, so now let's consider this matching. So in this matching, dog Harvard, cow Virginia. What can we say about this matching? Thankfully, both students get to go to school. This is a privilege of our Western capitalist society. But it's not their preference. Yeah, so dog and cow don't get their top preference. That's right. What else? Yeah, in some sense, Neither party is happy, but this is true in an even stronger sense. Because a better matching that also matches both students to colleges would be this matching, right? Because the dog is going to prefer Virginia to Harvard. Virginia prefers the dog to the cow. So here are two unhappy parties. Unhappy one, unhappy two. Right? This one was unhappy and this one was unhappy. In some sense, this matching is unstable because there is a swap, there's a way to change this matching such that both the M and the W in this situation would prefer. Okay, so this brings up the notion of this is an instable or unstable matching. And so we say that S star, a matching S is unstable A matching S is unstable if there exists a pair that's not in S, okay? So let's go through this definition. A matching is unstable if there exists some pair M star and W star that's not in the matching. And if we look at how these pairs are matched in S, so M star is matched to W prime and W star is matched to M prime, and two conditions hold. M star prefers W star to their current match, and W star prefers M star to their current match. So the way you show an instability is you find a triple. You find a pair that's not in the matching and two pairs that are in the matching, such that this condition holds. Yeah? At this point, no. Yeah, the preferences of M prime and W prime do not matter. Here is a mutually beneficial swap. The man prefers it, and the woman prefers it to their current condition. So what the situation that you're bringing up is that possibly there are multiple stable matchings that some prefer one party and some prefer another party. Okay, so we say that of course S is unstable if such a pair exists, and of course the point is S is stable Okay, so stable matching is a matching that is not unstable. Right? Okay. Yeah, so So here's an example of a stable matching. So this is one stable matching, and to your point, what's another stable matching here? This is also stable, right? It's very easy to see in this situation because, in particular, in this matching, the M basically get their top preferences, and in this matching, the W get their top matches. So, of course, if everybody's matched with their top match, there's no way to create an instability. Right? This triple right here, an instability requires a triple where M prefers, someone else, and W star also prefers someone else. But of course, in the matching, if you're always matched with your top preferences, then there's no way for you to complain, right? But it goes to your point, which is that for a given set of inputs, there could possibly be two matchings, and this comes down to who makes the moves first, I guess, in life. All right. So the crazy thing that I hope to accomplish today. Today's the day before Thanksgiving. I know that a lot of people are eager to leave, so I wanted to prove something fun and also remarkable and also practical, which is that this crazy theorem, which is that no matter what the inputs are, as long as each of the participants, you have n participants and you have n men, n women, and they all specify full preferences, there always exists a stable matching. Okay? There always exists a way to match these parties so that nobody can complain in a way that in an obvious instability. Right? And the way that we're actually going to prove this, the reason why it comes up in an algorithms class, is the way that we're going to prove it is constructively. So we're actually going to produce it. We're going to give an algorithm that, for no matter what the input is, produces a stable matching. And that's kind of a cool way of proving some theorem. You could prove this theorem that there exists a stable matching using some sort of combinatorial argument or some sort of abstract argument. Just says, there has to be one. But I don't know how to find it. Here's a case where algorithms actually helps prove a nice mathematical theorem. The proof is, consider this procedure. And we're going to lay this procedure out on this very next slide. So we're going to say, start with an empty matching. So the algorithm is phrased, or sort of the whole theory of this type of study is phrased in the context of proposals. So men make proposals to women in this algorithm, and women can either accept or reject those proposals. Okay. So the start of the algorithm. While there exists some unmatched M who has not asked out everybody on his list, let W be the first woman on that list who he has not yet asked. Okay? If W is unpaired, then clearly make a match between M and W. Now here's the one part of subtlety. So if W is already matched at this point in the algorithm, and matched with some partner M prime, and W prefers M to M prime, what should we do? She should. Yes. So so this is our algorithm. Very intuitive and simple. It's kind of surprising that it actually comes up with, first of all, it comes up with the matching, and second of all, the matching that it produces is actually stable. Okay. That's it. Very cool, huh? Remember, economists came up with this. Very good question. Very good question. It's exactly what you should ask. Avi, this is total bunk. I don't believe it. In fact, after we go through an example of this, we're going to prove two things. First, we're going to prove that the algorithm finishes. And second, we're going to prove that the output of the algorithm is a perfect matching and that it's a stable matching. Okay? So first, let's go through the algorithm just to make sure we understand how it's working. All right? So, okay, here we go. So that's where this the handout actually comes into class. Okay? So let's go through this. So imagine we're going to, the algorithm says start with some M who has not asked out everybody on his list and who is unpaired. So Mr. Mouse looks like a good candidate. So Mr. Mouse asks UVA, his top candidate, to be matched. And since UVA is currently unmatched, we go ahead and form that match. So that's the first step of this algorithm. So the match looks like this after the first step. Okay. Next step, let's consider the dog. And notice that the dog, his first choice is also UVA. So dog is going to ask UVA, because that is what the algorithm suggests. And now UVA, looks like UVA is already matched. And so what do we do if UVA is already matched? The second condition, we ask, does UVA prefer the dog to the current mouse? Unfortunately, no. And so, poor dog, nothing happens, and has to basically cross off the list, right? So the first two lines of this algorithm say, let W be the first woman on M's list who he has not asked. So we're going to keep track of who he has asked and who he has not asked. Okay, so now let's go through, let's see, that's the second situation. Now let's consider the cow. So cow's first preference is Yale, and Yale is unpaired. So even though it's the number last choice, we are going to go ahead and pair up cow and Yale. Okay, so here comes the first question.
Why do we go over the cow and not
Because the algorithm says let M be an unmatched M who is not. So there's actually no, I can go through any order that I want.
So for stable matching, considering just one party has different.
No, in the stable matching problem, both parties express full preferences.
But when we come to a stable,
The output of the matching is going to be for every M, there's one W.
yeah, but that's like M's the best way to set up the question. It's like we're constructing a stable matching for like M's essentially, right? Like there'll be another stable matching for W.
So you're getting ahead of the situation, but what you're suggesting, remember 2 slides ago, I showed an example where there were 2 stable matchings.
Yeah.
Right? In this situation, there are 2 stable matchings.
Yeah.
Since the way that I formulated this algorithm, the then proposed, we'll get to this in a second, we're going to always come up with this matching. We can shift the algorithm a little bit and produce another matching. This comes back to my first comment about life lessons. You should seize the day, essentially. You'll see that if there's a bias in this algorithm that we'll talk about. Okay. So once we get to this second step right here, this is the point where the first interesting thing happens in this argument. So now let's consider the fish right here. The fish's top preference is UVA, but UVA is already matched. So now let's consider our second condition. UVA is currently matched to Mighty Mouse here, but UVA prefers the fish, and the fish just asked UVA. So what do we do? Yes. Basically, we break this guy up. We match this right here. We match this, and we break this one up. So in diagrammatic form, we do the following. UVA was matched, still remains matched, but now has a better match. Poor mouse guy has his heart broken. Okay, so spend 2 minutes with your neighbor, just going through the algorithm and doing the rest of it until we actually figure out a complete matching. Tell me what happens. The size of the matching scale. And you'll see that if we Okay, did everybody figure out the answer? Everybody comfortable enough with the running of the algorithm that essentially after a few more steps, you'll figure out that everybody gets their second choice except for the fish. And in this case, only Yale loses out, which actually, who really cares about that anyway? So now that you understand the algorithm finishes, or the algorithm, you saw an example on some particular input, let's analyze a few properties of this algorithm. So first, let's try to argue that the algorithm actually ends. It doesn't fall into the loop that you were worried about. How can we argue that?
So each M only looks at.
1 second. Can you try it again? Can you try another one?
So each M only asks each W once, which means it goes down for each M if you have each W, but it never comes back up and asks the same one. So you don't actually run into a loop. You just go down this function.
That's right. So that while loop, it's once an M is matched, it's not going to ask anymore. And at most, for each M, this loop is going to run n times. So that means that this algorithm must terminate after so since there are n women and n men, this means that the algorithm terminates after The algorithm terminates after n squared iterations of this loop. Does that make sense? Okay. Why is the output a matching? Okay, so we want to say that each m so if you look at this algorithm, the only time a pairing occurs is in that red line up there and in this red line right here. These red lines execute in this while loop, and the while loop only begins with an unmatched m. So certainly at that top m is unmatched at the time it's paired, and right here, m is unmatched at the time it's paired. So certainly each m only is paired with one w. Now, how can we argue that each w is only paired with one m? Yeah? You're answering a different question. I want to show that it's a matching. Meaning, how come there's some woman that can't be married to 5 men? What prevents that in this algorithm? Yeah.
If it turns out that W is already matched,
Yes. So the point here is that the answers to these questions are going to refer specifically to our algorithm. So the way I'm going to say this is that consider each time a pairing occurs. The pairing occurs at that red line, the top red line. At that point, W is unpaired. Okay? Or a pairing occurs right here in this second line. And when this happens, M has just been made single. So every time the pairing occurs, right before that pairing, the second before that pairing occurs, W is single. So this means that the output is a matching. Okay, now the final consideration, why is the output of size n? That goes to your point up there. Yeah? Certainly we start with equal number of men and women, but why does everybody get matched? So I would like to say it in this way, which you can also take as life advice. If there exists an unmatched M, some woman has not been asked. So clearly, if this woman is on the preference list, then the unmatched M will ask that woman and then be matched. So why is this so funny? mathematically not correct. Okay, so now comes the final point about this, the very cool point, which is that the output from this very simple algorithm actually produces a stable matching. Let's try to understand why that actually exists and why that's true. Okay, so suppose not. So that means there exists an M star, W star, and so this is not in S. Such that right, M star prefers right? Now let's try to reason why this shouldn't happen. Sorry? Okay, so suppose that the output is not stable. Okay, so the output, let's say, was S. The output was the set S. And suppose that the output is not stable, right? By definition of not being stable, that means that there exists some pair, M star W star, that's not in the output, and M star W prime, M prime W star that are in the output, and the following conditions happen. M star prefers W star to his current match, and W star prefers M star to their current match. Okay, so I would like you to spend the 5 minutes with your neighbor trying to reason the rest of this proof. So the hint are, you start from the definition of what it means to be unstable, and the observation is, consider the moment. This is in the output pair. So consider the moment that this pair is created in the execution of our algorithm. What we need to do is come up, say, because this happened, we must be able to conclude we're going to eventually come to a contradiction, which will, therefore mean that the output must be stable. Okay? So use this observation to drive a logical train that leads to some contradiction. The only things you can contradict are actually these facts right here. Okay, so spend a few minutes. Spend 3 minutes with your neighbors trying to come up with the rest of the argument. I'll be wandering around. Make sense? Yeah, so here's an example for almost choice. So that
The way that these got matched somewhere somehow, just kind of, I don't know what you start or after I one of these is getting into it, and then so because like this one makes this one. Yeah, but I don't think yeah, so I'm starting to, let's say we have time to start over, because it doesn't matter which word we do. I'm starting to consider this choice on it. Then we're gonna consider M prime. And then M prime is gonna ask the no confusion.
Okay. So, a few of you have come to this conclusion that at the moment M star and W prime are paired, M star had to be single, right? But he prefers W star, right? M prefers W star to W. So that means M star must have already asked W star. W star must have rejected M star in favor of M hat. Right? In other words, there must have been some other M hat that W preferred, okay? And then either later on, since we know that eventually M prime gets matched with W star, either this M hat's the same as M prime, or later on, W star has to reject M hat for this guy. Right? But in either case, poor M star is in fact dominated by M prime, which contradicts this statement. Does that argument make sense? What is very cool about this, so any questions about it? So the people who first proposed this were Gale and Shapley. They wrote this paper, I think it's 1962. I'll link it to the website. Even in their own paper, they said, this is a very cool argument because it's clearly a mathematical argument. It involves zero numbers in the entire proof of it. It talks about a real-world situation. And it just goes to show that all you actually need to do to succeed in math is just concentration. Because all it did is these are just like 4 seconds of proofs. You just have to concentrate enough to hold the logical argument in your head. A very cool display of the use of mathematics. Clearly a mathematical argument, but it's unlike a calculus or a discrete math summation. Like, there are no symbols in here that are, each of these symbols could just be replaced by prefers. Right? Very cool. Okay. Now, many of you have come to this question in various ways, which is, when there are multiple stable matchings, how do we actually, what does the algorithm actually do? So in this example, right, which I believe, it's the same example we talked about before, if the men propose, then the matching that we're going to get is basically, okay, but if the women propose, then we're going to get a different one. Right? It turns out that there's actually a very remarkable fact about this algorithm. So the other question that you might ask is, how come the order, what about the order in which this loop, this while loop, if I pick m in different order, will that lead to a different outcome? What's your instinct about that? If you change the order in which you select which person to match, do you think you could possibly end up with a different outcome? It'll be stable, but it'll be a different one. So for example, is there an advantage to being earlier to propose? Yeah, intuition is right. We're going to actually prove this remarkable theorem that so the order, the time at which you propose really doesn't matter. The advantage in this matching situation is the fact that you do propose, which is again why I recommend you seize the day. All right, so the remarkable theorem we're going to show is the following. So we're going to add a few definitions. We're going to say that W is valid for M. Okay? In other words, W is in M's league, so to say, if there exists some stable matching So W is valid for M if there exists some stable matching such that MW is in that matching. Okay. Best M is So the best M is kind of what it sounds like. It's the woman, it's the W, such that MW is a valid matching, but every other woman that M prefers is not valid. So now we can define this matching right here. We can define this set right here, which is essentially for every M, you find the best matching for M. Right? The best matching means the person that is valid and no one better is valid. Okay? And it turns out, here's the theorem. Every execution of Gale-Shapley returns this matching. First of all, it's remarkable that this is even a stable matching. If you consider essentially the best matching for each M, you assign M to their best matching, showing that that's a stable matching is kind of cool. Turns out this algorithm actually returns that one. Okay? Shall we see why that's true? Yeah, so another way to say this is it's man optimal. Okay, and okay, so So consider some execution E of Gale-Shapley that returns S that's not equal to S star. Okay. So some man is not matched with their best valid match. Right? That's what it means for S to not be S star. Okay? So in particular, that means some W must have rejected a valid M. So consider the first time so that means that either, there are two ways for this to happen, right? There are two ways for this line to happen, right? So either M asked and was rejected, or M was originally matched with W, but now he's been broken up. So at this point, after one of these two events, M is going to be matched with some other, W is going to be matched with some M prime. Right? And but W is valid for M, so there exists some matching. Question. Who does M prime match with in this matching S prime? It's not W, right? So in the matching in S, what we're considering S here, there at this point M prime and W are matched. But in this other matching S prime, who could M prime be matched with? So what we want to say is that let's call this person M prime, sure, let's call him M prime W prime. And now, okay, now here's the trick. Since this is the first rejection, it's the first time someone W has rejected a valid M, certainly W prime could not have rejected M prime at this point. Where in this algorithm? So consider some execution E. And I'm going to stipulate that this execution E is going to produce some result S that's different from the man optimal. And now I'm going to consider this execution. I want to come to some contradiction. So this execution E, it has to be that there's some M that's not matched with their best valid match, right? Because in particular, this is the best match. So that means that some W had to reject a valid M. Yeah, but rejection can happen in two ways. Either ask to reject or break up. Yeah. The rejection is either I'm already paired it and I'm going to I'm not going to, so ask and reject is some unpaired M asked, yeah, or I was broken up, and that's also the first rejection. So there had to be some rejection. That's what we're analyzing. And at that point of that rejection, we're going to consider the first one. We're going to analyze that first one, okay? And then the result is after that first rejection, we had to create some pair like this, right? But it's also the case that we're only considering valid rejections. So since these two have been valid, this is the point that we're going to come to contradiction. Since these two are valid, there had to be some matching in which they were matched. And in that matching, M prime had to match with someone else. Okay? And what we're going to say is that it couldn't have been, in this execution, W prime could not have rejected M prime. Okay? And so okay, we're one sentence away, but now I've lost my train of thought as well. All right, I've somehow lost, now I sort of understand how you might feel in this class. Something might be as clear as day to me just 5 minutes ago when I started, and now I get the tension of having all your eyes at me. So this is certainly a true theorem. I got to fix it. I will post a write-up on the blog with a note with this. The point that I wanted to make in the last few minutes, I wanted to make 2 points, which is that so the Gill Shapley matching is going to be man optimal. Okay, and it just so happens that the man optimal So the man optimal matching is the worst possible stable matching for women, and vice versa. The woman optimal matching is the worst possible stable matching for men. Why does this actually matter? It turns out that if you're planning to become a doctor, this matching algorithm forms the basis of how medical residents are matched to hospitals. So originally, the entire history of this problem was that just like with many situations where lots of students are applying to lots of fixed number of positions, there could be some chaos. You might have had this your freshman year too, which is that you applied to a bunch of, or before your freshman year, you applied to a bunch of schools and you had some preference list, you were accepted at a few, and you had some preference list, and you were on the waiting list for some other schools, and so you're trying to decide where to go. And you might have seen this chaos, which is that some people start taking their positions, or some people start taking certain positions and releasing other ones. And as a result, a college might call you and say, hey, you were on the waiting list, you've been accepted, and then you might have just that previous day accepted in another spot where you weren't so happy with it. So now that a day later you discover that you had a better option, you might call that other place and say, actually, I rescind my acceptance, I'm going somewhere else. I actually had a friend in college who did this crazy thing. He actually registered at 2 places, and they started at different times. And he spent his money and basically went to both, took both slots. Very, very bad thing to do. He was eventually a Rhodes Scholar, so. And now works for a very wealthy oil family. No, one started earlier than the other one. So he went to the first one for a few weeks, didn't like it, and then went to the other one. Yeah, and got the money back from the first one. It's crazy. Yeah, so. In any case, the point is that these type of decisions have cascading consequences. One person decides to go here and reject all the other places, which creates openings in other spots, which etc. This happened in the labor market for medical residencies, and it became so crazy that residents were basically matching in their second year of medical school. They're making deals outside of their sort of studies to go to certain internships in their second year. And so Gale and Shapley studied this problem. They said that this is causing chaos and causing slots at the end of this to be left empty. So they decided to centralize everything and create this kind of stable matching algorithm. And they ran that matching for several years until they realized that this matching was always in favor of the hospital. And that was unfair. Additionally, it also didn't deal with the situation where a man and a woman who were married were partners. They needed to be at the same residency. So this algorithm doesn't work when you add additional constraints, like these 2 people need to be in the same spot. You can no longer guarantee stable matching, and the problem matching becomes incomplete. So in any case, it's a very rich problem, and it's used, if you're going to become a doctor, it's used to determine basically your future. Everybody have an excellent Thanksgiving. I'll see you next week.